Let's begin. Welcome, everyone. A couple of announcements first. So Ariana, we decided that instead of Ariana's having live office hours, she's going to record whatever she prepared for you as review. She's going to record it and upload it. Okay, and then Ainsley will still have her help session. So we will have a balance between both. For those of you who might not be able to attend today or join in, we thought this would be a great way to balance the effectiveness of these things. So thanks to Ariana and Ainsley for doing this. This is really above and beyond what I asked them to do. Yeah, thank you. And for the exam, I will send out more information today with the number of questions, what to expect in terms of questions. So you'll have multiple choice, you'll have numerical calculations, you'll have a few essay questions where you have to type an answer that we will review, and you will have a bonus question. There's about total between 20 to 24 questions. They're low stakes questions, and you will be getting one attempt, but for the full duration of the class hour. So an hour and 20 minutes. The exam shouldn't take more than a quarter of that time, but you're welcome to do it and just leave because there's no lecture after that, obviously. But you'll have that full session. I'll just finalize the timing before I send it out, but that's where we're headed to. And yeah, that's it. If you see me in the office, I am in the office this week. The kids are sick, so I might have to switch to home tomorrow if I have to stay home, but I'll be on Zoom, so you can still reach out by email if you cannot make it in person. We will answer you as immediately, as quickly as possible. So whatever is needed, and I plan on being here this week. So if you see me, just come by and talk to me, okay? As we prep for the exam. Now, I know the last thing on your mind now is to go through one more lecture that is unrelated to the exam. But I want to get this out of the way so that after the break, we come and hit the ground running with regression. So this will be the last lecture on interpolation. And we left off last time when we talked about high-order interpolation. Remember, an interpolant is a curve that goes through each and every point of data that we are trying to model the behavior in between any two data points, all right? And we studied linear interpolation as the simplest model. Then we went to quadratic and then qubit. Then we generalized to an arbitrary interpolant for n plus 1 points, data points. We said you can fit an nth order interpolant. The coefficients are what we're after. So although the polynomial is a nonlinear function, the resulting system of equations was linear. So our objective was to solve for the unknowns. And so we went through this exercise last time. And we showed that to obtain the coefficients, lo and behold, you have to solve a system of linear equations. Now, in this case, this is a very dense, it's a full matrix, okay? It's a full system of equations. So you will need to use a direct solver to solve it. We know how to do that. However, I will not be asking you, we'll not be doing this in the homework. We will be using built-in tools in Python. And in the end, I'm going to show you that polynomial interpolation is a terrible idea. Okay, don't go beyond quadratic or cubic at best, and we'll learn about splines as well at the end of the lecture. But to get there, I want to demonstrate why polynomial interpolation is a bad idea. And the function that we will be using is going to be helpful when we do regression. So let's go ahead and Pythonify this thing for an arbitrary polynomial. So you're given n plus 1 points. You can fit at most an nth order polynomial. So you get 2 points. You can fit a first order polynomial, which is a straight line. You have 3 points. You can fit a quadratic, which is a second order polynomial, and so on. So the function to use in Python, there are two functions that we will need. Both come from NumPy. The first one is called polyfit, and the other one is called polyval. Poly stands for polynomial. Polyfit means fit a polynomial. All right. Now, polyfit, we have to do this in two stages. The first one is to call polyfit on the given data, which is the xi and yi data. So those are the pairs, x and y, x1, y1, x2, y2, etc. You give them as separate arrays, the set of data for the x values, which are the independent variables, and the set of data for the y values, the dependent variables. And degree is the order of the polynomial that you want to fit. Now, for the intents and purposes of interpolation, degree needs to be equal to the number of points minus 1. Or if you get n plus 1 points, that's degree is equal to n. If you put anything other than n, you'll get regression. We don't know what that means yet. Okay, so don't do that. For right now, degree needs to be equal to the total number of points minus 1. All right? So if you put that, then what polyfit does, it solves that linear system I showed you in the previous slides. Okay, and what does it solve it for? It solves it for these coefficients, a0, a1, all the way to an. All right? So P on the left-hand side here, P equal polyfit xi, yi degree, P contains an array of the coefficients for an nth order polynomial. Okay? So now, with the coefficients, you can build a routine that solves the polynomial. You can put P0 plus P1 times x plus P2 times x squared, and so on and so forth. But instead of having to do that every time, Python provides a tool to take an array of coefficients and make a polynomial out of it, and that's called polyval. And it stands for evaluate a polynomial, or the value of a polynomial. Polyval takes two arguments: the coefficients of a polynomial p, which you solved for from the first line, and xe is your target value. Where do you want to compute? Where do you want to evaluate that polynomial? Okay? So in the example of the temperature and the density, right? It's like we were at 412 or 415 or 450. It's also possible to provide an array of values for xe, okay? Just like we did with interp, okay? With the standard interpolation for 1D. Okay? Now this will degenerate to give you the 1D interpolation. Okay, so if you have two data points, right? But it won't do a full linear interpolation on a full set of data points. Remember, when we did it on a full set of data points previously, it was doing a straight line between every 2 points. This one, your degree needs to be equal to the number of points minus 1 for it to do a full polynomial interpolation. And the return value of polyval includes the values that you want to evaluate. So best thing is to just do this by hand. So let's go ahead and grab that same notebook we were working with last time. We already have the data in there. We got everything. We can continue from where we left off. All right. Okay, so if you recall, all right, so if you recall, we had these data for temperature and density, and we plotted the data, we visualized it, everything should be filled up, and we did linear interpolation here. Okay, pop, pop, pop. And then we did the reverse interpolation, where we had to sort the data, right, in increasing order, when we swapped the meaning of the dependent and independent variables. So we did all of that. Now we are at polynomial interpolation. Now we are going to attempt to do a polynomial interpolant on the density temperature data set for air. Okay, so we are going to import polyfit and polyval. And remember, polyfit solves, given xi and yi data and a degree, polynomial degree, it solves for the coefficients of the system of equations. Since we are doing interpolation, degree needs to be exactly equal to the number of data points minus 1. Okay? So the first argument was x, or in this case, we were doing the temperature, right, as our x data point, right? So we're going to do t here. It's for the first question mark. For the second question mark, we had rho, the density. Now, for degree, what should we put? What was the total number of points minus 1? So how many points do we have? Yes? Length of t minus 1 or length of rho minus 1. Okay, so how do you get the number of points? You simply use the function called len. Len means length of an array. So len t gives you 19 points, or len rho is also 19 points. Okay? So for degree, for the polynomial, we need len of t or rho minus 1. Or you can say, degree is equal len t minus 1, and you use that here. Okay? Degree. Now, if you run this, it barks at you, and we'll explain that later. It says polyfit may be poorly conditioned. There's a lot of reasons for that, because polynomial interpolation is a very bad idea. But it does work. Okay? So now polyfit returns a bunch of coefficients. Okay? What is stored in the coefficients? In coefs, just print it. Okay? So if you print coefs, what you'll get is a bunch of coefficients, a naught, a1, a2, a3. In fact, it starts the other way around. This would be a naught, this would be a1, a2, a3, etc., all the way to this number. Now notice, this would be the coefficient of x to the power 18. Okay? And now you can see a problem, x to the power 18, and you're multiplying it with a number that's 10 to the minus 42. You see the problem with polynomial interpolants. The higher the order of the polynomial, the larger the numbers are going to be. The smaller the coefficients, they're below round off. So they are really, really uncomputable in many cases. Anyway, so let's take this at face value for what it is. Know that coefs here contains the coefficients of the polynomial we're trying to fit. So again, we're trying to fit a polynomial of degree 18. So that's a naught plus a1x plus a2x squared, etc., plus 18x to the power 18. Okay? So these are the coefficients. To evaluate the temperature, the density at some temperature, T equal 412 and 415, we simply use polyval. And we do, for polyval, you need to give it the coefficients. Okay, so it shows you here the function signature. Parameters, 1D array of polynomial coefficients. Okay, so that's all. We already have that from polyfit. So we have coefs over here, and I want this at 412 and 415. I want the density in those two values. Bam, it gave me those two densities: 0.84, 7, and 0.841. All right. Okay. So now we know how to use polyval. Now let's go and evaluate at 980. So polyval, coefs, put 980 here. See what you get. Did you get a number? What was it? For the density, right? Yeah, we're interpolating the density. Okay, so what did you get here? So this is saying, using polynomial interpolation, the density at 980 kelvins is, what did you get? Yeah. Does that make sense? No, absolutely not. Densities cannot be negative. So something is messed up. We did the interpolation. Okay? By definition, it should go through each and every point. But somehow at 980, it's messed up. Okay? So what do we do in this case? Let's go ahead and visualize this interpolant. See what it's doing between the data points. Okay? So I'm going to create an array of temperatures. So I'm going to go tvals, let's say, mp.linspace. I want to plot this interpolant, okay? So if I were to plot the interpolant on the original data points, it will go through each one of those data points. Don't you agree? That's by definition. Okay, so let's do that actually. So plot the polynomial interpolant, the 18th order on the input points. It should go through each one of those, okay? So if I were to say plt.plot for the temperature values and then polyval coefs at the temperature values, at those input temperature values, all right? Okay, so it's going to give me something like this, and I'm going to do it as a scatter. Okay, so black dots, okay. Now, if I were to plot the original data, plt.plot, t and rho, okay, and I'm going to do them squares, blue squares. Okay, they're on top of each other, okay? You can't tell the difference. They are on top of each other. Indeed, by definition, because the polynomial interpolant needs, the value of the polynomial interpolant needs to be equal to the value of the input data. But something is happening in between those data points. To be able to see that, we need to create points between the input data. So I'm going to create an array of values, t values, let's say mp.linspace, and we're going from 100 to 1000 because that's the temperature range we obtained. And I'm going to put like 200 points in between. And then I'm going to do plt.plot t values and then evaluate that polynomial at those t values. Because now I have so many points between the discrete data, I'm able to see the behavior of this polynomial in between the data points. When we had a linear interpolant, what was the behavior between any 2 points? Okay, that's an exam question. What's the behavior for a linear interpolant between 2 points? Straight line. For a polynomial, it's going to be something different. This is an 18th degree polynomial. What that means is that that polynomial has at least 18 roots. Has 18 roots, exactly. So it's going to cross the x-axis 18 times. So and there's no guarantee that it's not going to cross the x-axis between any 2 points that you're interpolating in between. So let's see what happens. I'm going to go back, plot the original data here, and then plot the polynomial. All right, so look what's happening. Indeed, the polynomial goes through each and every data point, right? They're the blue squares. It crosses them spot on. But then initially, look, it jumps a little bit and then goes down. But then when we get here to high values of the temperature, it goes up and then dips, crosses the x-axis, hits 2 roots, goes negative, hits 2 roots, and comes back up. That's the problem with high-order polynomial interpolant. You think you might be accomplishing a great feat, but you're actually causing more problems because, by definition, polynomials have to have as many roots as their degree. This is an 18th order polynomial. It has to cross the x-axis 18 times. Real space or imaginary space, it has to have those 18 roots. It just so happened here that it crossed this x-axis between those last two points. So there's no guarantee for high-order polynomial interpolants to remain bounded within your data set. They are highly oscillatory. They are problematic. In practice, you never use a polynomial interpolant higher than order 2 or order 3 tops, okay? Because of these issues. So what you take out of this is that high-order polynomial interpolation is a terrible idea because those polynomials are highly oscillatory. They could go up, negative, positive, in between any 2 data points. You might overshoot or undershoot your values. Yes, Dan? It will be doesn't make sense because you're trying to fit a polynomial of order 23, but you only have 19 data points. Where are you going to constrain? What are going to be the equations for those additional points? Now, if you go ahead and put 2 or 3, that becomes regression, which is what we're covering here. Okay, then you would be fitting, a straight line over 19 points. How can you fit a straight line between 19 points? That's regression. We're going to talk about that after the break, okay? And we're going to be using polyfit, by the way. So that's why I want to introduce polyfit here. But that's the problem with these polynomial interpolants. They are unreliable. You don't use them. Okay? They cause a lot of problems. So, and it kind of makes sense because there's like x to the power 18, and then you throw in a temperature value of 980 to the power 18, and then multiplied by a coefficient that's 10 to the minus 42. That's like, there's no way this calculation is going to be accurate at all. So it's a bad idea. Don't do high-order polynomial interpolants. All right? If you insist on doing interpolation, either do linear interpolation or local quadratic interpolation. If you want to do cubic, I'll teach you about splines, which are the best type of interpolant ever. All right? So, unfortunately, it's not straightforward Python to apply local polyfit. Okay, so the alternative to such high-order polynomial interpolant is to go locally and pick, if you want to do quadratic interpolation, you need to locally pick 3 points together, right? Because for quadratic, order 2, you need 3 points. So you pick 3 points and interpolate between those 3 points and then move on. Unfortunately, programmatically, that's hard because you would have to search your array, find those 3 points, figure out the interpolation. And Python doesn't provide any of those features readily. So we're kind of stuck with polyfit. So this is how you would do it. So for example, this is data, same data, temperature, and then you have density, you have thermal expansion coefficient, and then you have, like diffusion coefficient, and then you have your viscosity. And let's say you want to find the viscosity at 412. You could use for linear interpolation, you use those 2 points, you take the 2 values, and you do the interpolation. For quadratic, you have to solve that system of equations by hand. You get 3 equations, 3 unknowns. And then, at 412, I would use those 3 points between 400, 450, or 500. Or you could use 350, 400, and 450. It doesn't really matter in that case. For cubic interpolation, you would need 4 points, right? Because a cubic has 4 unknowns, A0, A1, A2, A3. Right? So you need 4 points, 4 equations to get that. Now, the best alternative to this, so in practice, what I do, I either use linear interpolation or cubic interpolation, but not like this. I use something like a backdoor cubic interpolation in Python because I don't want to do it locally. I don't want to have to worry over an array, go search it, find the points that straddle my point in question, and figure out all that math. I want something that does it for the entire data set. That's where cubic splines come from. Are you familiar with splines? Have you heard that word? If you're doing any graphic design, if you design chips, or if you've designed guitars or like violins, etc., those curves that they make with wood, right? They're so hard to make, but what they do, they take a pliable piece of wood, they wear it a little bit, even when they're designing ships. They anchor some points, and then they weave the wood around it. Those are called splines. You can do the same procedure with any number of data sets, any number of data points, sorry, except that you say, okay, I'm going to put a cubic between each pair of 2 points. Now, that's weird because you have 2 points, so you only have two pieces of data at those points, right? How can you put a cubic which has 4 unknowns in it? Well, you come up with additional conditions. So here's an example. Let's say I have these 4 data points, x1, y1, x2, y2, x3, y3, x4, y4, and I want to weave a cubic polynomial between each pair of points. So this is a cubic, this is a cubic, and this is a cubic. Okay? So let's see how the math works out. So for that first cubic between the first 2 points, let's call it f1. Okay? It's got a1 x cubed plus b1 x squared plus c1 x plus d1. Okay? For the second cubic between x2 and x3, and y2 and y3, let's call that cubic f2. So it's got also 4 coefficients, A2, B2, C2, and D2, right? Remember, the coefficients are the unknowns in this case. And finally, that last cubic between the last 2 points, let's call it F3, it also has 4 unknowns, okay? So now in total, we have 4 unknowns for this one, 4 unknowns for that one, 4 unknowns for that one. So we have a total of 12 unknowns. Now you can imagine as you scale this, let's say you have 50 points or 100 points, right? For each pair of points, you have 4 unknowns. So in general, for n plus 1 data points, you can build n splines, right? In between every pair, you can build n splines, and you must satisfy 4 variables per spline. Those are the 4 unknowns. So we need to figure out a way to come up with 4 times n equations, right? So in this particular example, we need 12 equations. You need to know this. I'm not going to ask you how to solve for splines. It's really hard. But you need to know how to get the conditions. The conditions are really easy to get. Okay. So let's see how we can figure out how we can get those additional equations. Okay. First, we know that the first and last points, these two here, this spline and this spline, they must pass through these points. So in other words, f1 at x1 needs to be equal to y1, and f3 at x4 needs to be equal to y4. Okay, so that gives us 2 equations, right? We are on the lookout for 4n equations, right? Now, at each interior data point, again, each one of those splines needs to be equal to that value, because by definition, an interpolant needs to pass through that data point. So take this interior point, for example. This red function, this red spline, needs to be equal to y2 at x2. And so is this green one. Needs to be equal to y2 at x2. At this point, this guy needs to be equal to y3, and that guy needs to be equal to y3. So overall, you get 2 times n minus 1 additional equations, right? So we're building to get to 4n. Okay, so now we're done with just the function values, but that's not enough. Okay, that's not enough. We need more equations. So what do we go after? We go after the derivatives. We say that at each interior point, the functions need to be continuous in their derivatives as well. So we make, at each interior point, we make the derivatives equal. We make the derivative of the red function at x2 equal to the derivative of the green function at x2. So f1 prime at x2 equal f2 prime at x2. You can differentiate this by hand. Yes?
Why is it n minus 1 and not n minus 2 for the interior?
For the interior points, for this one?
And for the one before it.
Yeah, so 2n minus 1. These are the interior points. Right, so you have n plus 1 points. You can put n splines and n minus 1 interior points. So you have n minus 1 interior points. N plus 1 is the number of points. Right, so yeah. It's kind of gets like sometimes I use n, and then you get. So just keep counting. Whether you start with n plus 1 or n is just semantics, right? But we're starting with n plus 1 points. You have n splines because it's easier to reason with n splines, right? That's why I chose n plus 1. Okay. So you have n minus 1 interior points, or just count them. Okay. So if you match the derivatives, you get n minus 1 constraints. We still need more. We still need n plus 1 constraints. So we match the second derivatives. So what does it mean when we say we match the second derivative? You take the derivative of f1, which is 3a1x squared plus 2b1x plus c1, equal to 3a2x squared plus 2b2x plus c2. And you set that, you put those equal, and you come up with you have one more equation for the unknowns. And that becomes part of the system of equations. Okay, you just add those to the system of equations. You have unknowns, knowns, you build your system of equations. And finally, we still are missing 2 more constraints. We set the second derivatives to be equal to 0 at the endpoints. Okay, we say that last function, f double prime 3 at x4 is 0, and f double prime 1 at x1 is equal to 0, and you get a total of 4 constraints. That's a lot of work to do, right, to come up with this system of equations, etc. Python does that all for you, as I'll show you in a second. So in our example here, we had 4 data points, Therefore, 3 splines, 4 unknowns per spline, so that means 12 constraints. This is how it will work. So first and last splines must pass through the first and last points respectively. What that means is f1 at x1 is equal to y1, and f3 at x4 is equal to y4. You really have to do this by hand for it to stick. Okay, so as you study, as you learn this, go and do it by hand. Otherwise, it's not going to stick in your mind. Okay, the second condition is that each and every spline must pass through the interior points, and therefore the red function at x2 equal y2, the green function at x2 equal y2, the green function at x3 is equal to y3, and the purple function at x3 equal to y3, right? So you expand that, you write it out in terms of a1, b1, b2, etc., and you get more and more equations. Then you match the derivatives at the interior points. Derivative of the red function at x2 equal to the derivative of the green function at x2, and so on. And finally, the second derivatives as well. And at last, you set the second derivatives at the endpoints to be equal to 0. All right. That's a lot of conditions. Yes?
Why do we stop at the second? Like, why does...
That's enough. That's enough unknowns we have. Yeah. So it makes sense, right? So because continuity of functions, you start with the value of the function itself, then first derivatives, then second derivatives, you go by order. Doesn't make sense to skip derivatives, to go from first order to third order, right? Doesn't make sense. Like, because it's a stronger condition to satisfy continuity on first, second, and third, and so on. Yeah?
If we're setting with number 5, does that mean that, does the implication of that mean that our bit only fits between those two data points?
Yes. Interpolation is always between the endpoints, never beyond. So don't extrapolate. Now, there are other conditions at the endpoints if you have more information about the second derivative is hard to think about, but if you have more conditions at the endpoints, you could choose to match the first derivative maybe, make it go flat, but you're not going to get nice splines in that case. Really, these conditions are like arbitrary. They're the best that could give you stable splines. There are many advantages to splines. They are always smooth, more accurate than linear interpolation, doesn't get oscillatory because it's a third order polynomial between any 2 points. So although it has 3 roots, if the points are close enough, it's unlikely that it's going to go and change sign on you. So they're nice and stable. And, you know, they use them to make ships. So, all right. Now, to do splines, we cannot use NumPy. We have to use SciPy. So here's kind of the syntax. Again, you have to do it in 2 steps, like polyfit. From SciPy.interpolate, go figure, just take this for what it is. Import cubic spline. So cubic spline is a set of routines that does all of what I showed you in the previous slides. It does it for you. It goes, builds the system of equations, figures out, assigns a spline formula for every pair of points. Remember, what you're building here is a different cubic polynomial between each pair of points. Okay? And it does all of that for you just given the input data, the x and the y values. So you call cubic spline, you store it in an object called CS. Now that does not contain the coefficients of the splines. It contains more than that. It contains the coefficients of the splines and also where each spline fits between which 2 points, right? So you need that information. And then finally, you evaluate the spline at a variable of interest. You say CS, whatever that function did. You call it on the value of interest, and it gives you a value, all right? And those could be arrays, okay? Those could be arrays. So let's go back on Canvas and do the cubic spline here, right? Not on Canvas, sorry, on Python. So from SciPy.interpolate, import cubic spline. It's giving me the star of death here. Okay. All right. So for cubic spline, what do you need? You need the x data and the y data. In this case, temperature and density. All right. Oops. Temperature and density. When you do this, no warnings, no issues. CS contains a bunch of things if you want to print it. Yeah, it's an object of type cubic spline. it does something, contains all the information about the splines, all the nasty stuff we were trying to do previously. All right, so now let's evaluate the temperature at the density at 412. You just simply call this object CS at 412. And it gives you a value 0.846. Yep, that makes sense. Now we had an issue with 980, with the 18th order polynomial. So if we now evaluate the spline at 980, it gives us a value that is at least not negative, 0.33. All right? So what I have here is a plot of the spline. And if you plot the spline, it looks gorgeous. It's putting a cubic between every 2 points. It must pass through each and every point by definition. If you've taken stats and you've studied regression, you'll know that the regression line, you're lucky if it passes through 1 point of your data set. It shouldn't, in fact, pass through any 1 point specifically, because you don't want to bias your analysis. But interpolants are completely different. They're just trying to fit in between the data. I don't even like to call them fit, just interpolate between the data. Okay? Cubic splines are my favorite type of interpolant. They're so easy to use, okay? And you have the recipe now to use them in Python. Now, these slides, these notebooks, they will be your go-to. Next year, they're going to be your go-to. Don't go into mass transfer or heat transfer or thermal, and you're like, oh, how do I solve a nonlinear equation? You have it here. Come back to the slides, come back to the lecture, and just use this material. And trust me, it's going to get you the answer. Gavin.
So when do you use interpolation to regression?
That's a great question. We will address it when we hit regression. But for now, because I know you're going to keep asking me that question, so you use interpolation when your data comes from a deterministic or a kind of straightforward process. Like density and temperature, it's obvious. It's not like the density. There's no variation in the density as a function of temperature, right? But whereas, height versus age, right? If somebody is 18 or 24, that's not a strong predictor of height, right? Yet you can plot the data and you see like a scatter of the data, right? Or you could say femur length versus height. There's a strong correlation between femur length and height, but it's not as strong as density and temperature. So when you plot those data, you'll see like a scatter. You'll see a trend. You cannot fit one line between them. For one femur height, for one femur length, you can get 2 heights, for example. So what do you do in that case? You say, you know what? I'm going to model the data. It looks cubic, or it looks like a straight line. So you use regression in that case. You can't interpolate in that case. But in this case, your data is very clean. It's 1-to-1. Temperature, density, you saw it just coming down nicely and neatly. Interpolation is the answer. It would be silly to do regression here. Okay? Regression, because it's not a statistical problem. This is a deterministic and accurate representation of the data, right? So you do I answered the question, actually. So was this helpful? Okay. All right. Up next, we're almost done with interpolation. But next, I want to give you. You're going to come back to this next year, I know, so I figured I'll just at least introduce it to you here. Interpolation doesn't only work in 1D, it works in any dimension. And why would you have, what do I mean by multiple dimensions? I don't necessarily mean X, Y, Z, and temperature. I mean actual data, like pressure as a function of temperature and density and viscosity, for example. That's a multi-dimensional table. Here's an example of pressure and temperature, okay, for water. So, and looking at the specific volume, which is 1 over the density, how many cubic meters can 1 kilogram occupy? The specific volume of water at various pressure and temperature values. Okay, so you have 2 variables here, 2 independent variables, because the specific volume or the density of water depends on those 2 quantities thermodynamically. Okay, so you have this table, You do experiments and you have this table, and then the question is, what if you want to find the specific volume between these 2 points at 0.75 bar and 175 degrees? Okay, so you have these two values in the table, and you kind of want to interpolate between them. You can't average because the other points are not always in the middle. Like, well, this example, 175 and 0.75 is right in the middle, so you could take the average. But in many cases, it's not. What if you're doing it at 180 and 0.7, for example? Right? So you have to do multidimensional interpolation. In these cases, the simplest kind of interpolation, the one that's most robust, is actually linear. Anything beyond that becomes so complicated. Like, imagine fitting a quadratic in multiple dimensions with multiple variables. It's just, the complexity just explodes exponentially. So I will just describe the process to you. You're not responsible for that. This used to be a bonus problem on the exam. But now I just kind of give you the procedure of how it's done. So this is FYI, for your information. All you need to understand is like, okay, how does that there is 2D interpolation or 3D, etc., and how is it done? You interpolate in one direction at a time. So suppose you have, what I'm showing here is this table I showed you previously. You'd have temperature, pressure, for example, and a bunch of values. Okay? You want to interpolate between those values to obtain, let's say this one, something here. All right? So find this value. What do? One way to do it is to first interpolate in the y direction. So interpolate those two values there, And how do you do this? You just do linear interpolation. It's a 1D problem. So break it down into two 1D problems. So this is a 1D problem, and then one last 1D problem, and you get that red point. Or you could do it in X, 1D interpolation, and then you get to the two-dimensional interpolation. In any case, it looks like this. It's kind of very complicated just for this simple case. Linear and already pretty complicated. Now, we're not going to do this, but I will give you the code for how to do it in Python. And there's a great coding example. So this explains what you need to do in this case. It's called, just like polyfit, there's something called interp2D, just like interp for a 1D case. There's interp2D that interpolates a table for you. So this is what 2D interpolation would do for you. Imagine you had temperature data on a heated plate. Actually, I have a capstone project working on something like this now. They have a heated plate. They can measure the temperature. Like, we could only afford like 10 sensors, right? So we measure the temperature profile on that plate. But then with 2D interpolation, you can turn this into this. You're not generating more information, but you're like making it at least look nicer and smoother. Okay? There's an example for what to do here. I know you will use it next year. It's kind of premature to cover it now, but I at least want you to have that tool for when you go to heat transfer. Okay? All right. Let's resume, please. So this last part of the discussion, I think, is very important to start setting the stage for regression. Okay? As you saw, as we've been doing now so far, there's no reason to limit ourselves to a straight line or a polynomial or a cubic. That was completely an arbitrary choice. It was useful because polynomials are dense. They're everywhere. They're dense in the real space, in the function space. You can always find a polynomial, but they're also problematic. But sometimes you know a little bit more about your data. What if it varies according to some sinusoidal profile? Like, the temperature cycling with the sun rising and setting, you have some kind of sinusoidal process, right? So what if instead you want to interpolate using a sine or cosine? Or something more about your data that a polynomial is not going to do a good job for interpolation. Now, again, this discussion is to set the stage for regression. It's hardly used in interpolation, but it's a great segue to get the roots of regression popping in your head. So suppose now your model for the data is, instead of a naught plus a1x, you have a cosine x plus b log x. Could we do this? Could we do this? Yes, we can. So go ahead and try it. You have two data points now, x1, y1, x2, y2, and you have a model, a cosine x plus b log x. Okay, what are the unknowns? Hint, they're shown in red. Come up with the equations that you need to solve to find the unknowns. Now, this is an interpolant. So by definition, it needs to pass through each and every point. So do what we did with the polynomial. But do it for this model now. A cosine x plus b log x. Please try. Okay, now put it in. Put it in matrix form. Yep, you got it. Yeah, you have to. Yeah, I don't think you're thinking of drawing the function, and then no, you can't, because if you want to plot it on the imaginary plane, you need a third dimension to put the polynomial, because you need to plot the polynomial over the entire complex plane. So it would be a 3D plot. Yeah, because then the polynomial value over the real and imaginary axes, right? So you would need, or you could do contour plots. So you project that on the imaginary plane. All right, so let's see. What do we get? Equation 1, the first equation.
Y1 equals a cosine x1 plus b ln x1.
Okay, so what did you do to get that equation?
I just treated one ordered pair and just
Uh-huh.
the y with y goes as x, right?
Yeah, you made the model pass through that first point, right? So what your colleague did for the first equation is say, okay, now by definition, the interpolant has to go through each and every point. We have 2 points. We have 2 unknowns, a and b. Don't be scared by the cosine and log. They're going to be constants, okay? It's a nonlinear model, but the unknowns are a and b, not the cosine and the log. So your colleague passed this model through point 1. Point 1, the first point was the pair x1, y1. So by definition, if it passes through x1, the value needs to be equal to y1. So that's equation 1. Equation 2, same thing. Pass it through x2, right? There you go. You have 2 equations and 2 unknowns. Now you put this in matrix form. It is a system of linear equations. Again, cosines, logs, x squared, doesn't matter. The model is nonlinear, but it's linear in the unknowns. Okay? The unknowns are a and b, the coefficients. And there you go. You can do interpolation between 2 points, not necessarily as a straight line. Cosine plus log. So suppose you know more about your data between 2 points. I know 2 temperature values at our home between sunrise and sunset, and it's sinusoidal. I'm going to put a sine and cosine interpolant, not a straight line in between. It's probably going to be more accurate, maybe. Okay? Okay, great. So now, in general, what we did here, instead of using x, x squared, x cubed, etc., we used something else, cosine, log. You could use exponential, sine, whatever. Those functions are called basis functions. Okay? So that's the first time, maybe you've heard this word before, but here in this context, a basis function is an elementary function like 1, x, x squared, x cubed, cosine x, log x, square root of x, exponential x, that you use it with other basis functions to build a more complex function, a more complicated function. When you think about the polynomial, you were using 1, x, x squared, x cubed, blending them together so that you build a higher order polynomial, right? So in this case, these are the basis functions, cosine and log, and the parameters or the coefficients are a and b. Okay? From here onwards, and as we hit regression, we're going to be taking models with different basis functions. Why would you choose one basis function over another? Because it gives you power to model things that are not necessarily just polynomial. You might have more information about a process. Rather than putting a polynomial, put something that is more relevant to the process. When we get to regression, we will learn that bacteria grows according to a certain inverse square law. So we're going to fit a model that looks like that, except we don't know the coefficients. So we'll adjust the coefficients so that the model fits nicely. All right, so let's go through some examples of basis functions. OK, I'll start with the first one. A plus bx. The basis functions in that case are 1 and x. Yes, 1 is a function. Because you have a times 1, a is your parameter, plus b times x. B is the parameter or the coefficient. X is your basis function. Now, go ahead and write the basis functions for the rest. A naught, A1, A, and B are always coefficients or constants in this case, OK? So write down the basis functions. Put them in braces, like I showed you for the first example. All right, let's see. For a naught plus a1x plus a2x cubed, well, you guys have been answering a lot of questions. We're going to give the chance to some other groups. All right, Lions. Correct. So for this model, we have 1x and x cubed as our basis functions. All right, what about the next one? A naught plus a1x plus a2e to the minus x squared. Bernoulli, do you have? No? No? OK. Try. 1
x e to the x and x squared.
There's no e to the x, e to the minus x squared, right?
Oh, I would take that as just one function.
This one, that's one basis function,
Oh, okay.
right? So you're right. 1x e to the minus x squared. Again, a basis function is an elementary function, sine, cosine, log, whatever. Really, if you can separate the coefficients from the basis functions, from the functions that look like ugly and weird or complex, that's it. That's your basis function. OK, what about the one after it? You want to take that one? Yeah?
1 and ln of x.
Log x. That's correct. 1 and log x. What about the last one? The runs.
Cosine of t and the natural of t.
Correct. Okay? That's it. That's what basis functions are and what they do. Okay? You just take simple elementary functions, blend them together to make more complex functions. All right. Now, so far, we've been blending them linearly. Okay? We're just adding a coefficient times the function plus coefficient times another function and so on. We can do something more than that, as we will see later. But let's generalize now. In general, if you have a model with basis functions that are called, I'm going to call them phi. Phi1 of x plus phi2 of x plus etc. all the way m basis functions. So those could be 1x, x squared, x cubed, etc. They could be 1x, e to the minus x, log x. They could be cosine x, cosine 3x, log 2x, e to the minus x squared, 1. Okay? Anything, any basis functions. All right? This is very general. This is the most general model for interpolation. All right? Now, to interpolate this model, you have m basis functions or m coefficients. You need m data points. And simply, the system of equations is built by passing that model through each data point, through x1, which is equal to y1, through x2, which is equal to y2, through xm, which is equal to ym. That's it. There's your system of equations. Everything we studied so far is a special case of this. So in the exam, if I ask you, what is the system of equations for a naught plus ax plus bx cubed? Oh, easy. You just pass it through this or build it with this matrix, okay? And you get that system of equations. Because that always messes with the standard, because we learned to fit a polynomial without any missing coefficients. A naught plus a1x plus a2x squared plus a3x cubed. What if I give you a plus bx cubed? I'm missing the 2 in the middle. Well, you could fit this. You should be able to derive the equations just either using this matrix or just by hand. Okay? All right, so now let's build this up. Again, this is setting the stage for regression, because interpolation, anything beyond the cubic, it just gets really annoying. Like, you know, with the 18 data points that we had for the temperature, you would need like cosines and 18 sines and cosines, and that becomes just ridiculous. It's really unrealistic to do that. But I'm doing this because I want to set the stage for regression. Now, here's a nice way to think about this, and we're going to come back to this in regression, I promise you. So try to pay attention with me a little bit here. Just a little bit. So the way to think about this is that each column in this matrix corresponds to a basis function. Column 1 corresponds to the first basis function, column 2 to the second basis function, and so on, all the way to the mth basis function. Right? Now, the rows correspond to the data points. First data point is in the first row. So you get all the basis functions applied at the first data point in the first row. Remember, those are going to be actual values in the coefficient matrix. We're going to solve this matrix to get the coefficients of the polynomial, the second data point and the mth data point. OK, great. So that's for linear interpolation. Now, what if I ask you to do this? What if I give you 2 data points, x1, y1, x2, y2, and I ask you to interpolate between those 2 data points using this model? Alpha times hyperbolic tangent beta x. Just give me the equations for alpha and beta. Alpha and beta are the unknowns. So this is a situation where I know my data behaves as a hyperbolic tangent, but I need to tune that hyperbolic tangent. Is it, 2 10h3x or 0.7 10h 17x, right? So how do you fine tune it? We look for those 2 points, right? Alpha and beta. So just come up with the equations that govern alpha and beta for this case. Again, by definition, an interpolant needs to pass through each and every data point. Okay. So what is this? A system of nonlinear equations, right? Yeah. You use fsolve. Okay, equation 1. You got it? No? Okay, what did you do in the previous example? You passed the model through each point. Do it here. Okay, ninjas, any answer? Any progress? To do the what? No, just write the equations. What equations do we need to solve to find alpha and beta? So do you have the first one? Okay, so you put, you ran the model through x1 and y1. So what was equation 1? Just read it for me. Okay, so again, with interpolation, you just pass the model through the data points. That's it. So for point 1, for the first point, x1, y1, you pass the model through x1, it should be equal to y1. That's by definition, by construction. That's your first equation. Your second equation, you pass it through x2 and y2. Okay. Now, what is this? You have two equations and two unknowns. Alpha and beta are the unknowns. But do we know how to solve this? Yes. So what was the tool that we used? fsolve. So this is a system of nonlinear equations. Okay, when I told you about making connections between the things you're learning, these are the connections. This is interpolation. Yet we have nonlinear solvers in interpolation. Oftentimes, it all boils down to finding what equations you need to solve. Once you get to that, then you'll figure out the procedure. With linear interpolation, where the coefficients were outside the basis functions, we had a system of linear equations. Now, in this model, the beta is inside the hyperbolic tangent. It is nonlinear. We can't split it. You cannot write this in matrix form. Right? Beta is inside the hyperbolic tangent. It is a nonlinear system of equations. Then you put it in residual form and you solve it, just like we solve a system of equations. So that's called nonlinear interpolation. That's crazy. So we started with a straight line, polynomial, cubic splines, arbitrary basis functions, sines and cosines. And now we're doing nonlinear, which is like the most complex of all. All right? It's possible to combine basis functions in a manner that results in a nonlinear system of equations. Okay? And here's the definition. How can you tell if a model is linear and nonlinear? That is going to be quintessential when we hit regression, because nonlinear regression is one of the most powerful tools you can use to model real-life data. Okay? So that's what my objective is. A model interpolant will result in a linear system of equations for the coefficients of the basis functions if those coefficients show up linearly. Again, we are after alpha and beta and a and b. If those show up linearly, they're not under the action of some crazy function or complicated function, then it's going to be a linear model. Okay? All right, so here's a table. And I want you to take a few minutes to figure out. It's got a bunch of models, 2 data points, a bunch of models that I'm trying to interpolate between the 2 data points. Now, each model is going to result in 2 equations and 2 unknowns. The question is, are those equations linear or nonlinear in the unknowns? You don't even need to do math. You have to try to do it just from eyeballing it. Again, if the basis functions can be separated from the coefficients, then you have a linear system. If not, if the coefficients show up in the basis functions, inside them, then that's a problem. All right, first one, ax plus b. Linear? Yes. Basis functions are 1 and x, and a and b just can be separated from those. You can write the matrix, the system of equations, clean. Okay. What about ax plus b over x? Linear, right. Shut up, Siri. Okay. What about sine ax plus b? Nonlinear. Why? A is inside that nonlinear basis functions. Okay. X to the power a plus b. Okay. I heard someone say linear. Okay. Do you think it can be linear? We're not doing any transformations, but you're right. If you were, So your colleague is saying if you take the logarithm of that, maybe you could take the a out, but there's the plus b, so you can't really do that. We'll see something like it in regression. But okay, so it is nonlinear. A shows up very non-linearly over there. What about the one below it? A to the power x plus b. That's very nonlinear as well, right? Because that you can't separate a time, that a to the power x is just like embedded in that power. Okay. Now this one is fun. E to the power alpha times x plus beta x squared. Okay. Linear, but there was, okay, what about the rest? There's like 5 people said linear. What about the rest? What's annoying e to the power alpha, right? So what if you call e to the, Sarah?
Well, I was like, couldn't you just replace e to the alpha with a different constant?
That's right, exactly. Okay, that's it. E to the power alpha, e is just a number. To the power alpha is just another number. So e to the power alpha, call it capital A. And then the system becomes linear. All right. What about the last one? No logarithmic transformations. Beta e to the alpha x. Nonlinear. Exactly. Okay, good job, you guys. All right. That's it for interpolation. Okay? That's it for interpolation. You can go home and study.